We have the presentation of our colleagues from the Global Modeling and Assimilation Office of NASA, with whom we have been working from a long time, first at CTAQ and then of CanAIRy Alert. And the whole idea was, can we use the tools that they have developed of this GEOS-CF air quality forecast? What else is needed so cities can use those tools? So that's how CTAQ started. And now, over the last year and a half, we have been working on CanAIRy Alert, and we were focusing on 4 cities in Africa, Kampala, Kigali, Accra, and Nairobi, so they could also use the air quality forecast. So that's the overview, and that's why we are today. So thank you so much, Emma and Carl. We have also been in contact a lot with Christoph, who I think he's not able to join us today.
I think in the first 2 sessions today, we'll be giving a general overview of NASA data for air quality. In the first session, I'll be talking about some of the basics of satellite data for air quality, including basics of remote sensing, some satellite data products for aerosols, trace gases, and how to access these data. And then following hopefully a short break, in the second part, my colleague, Dr. Emma Knowland, will talk about the GEOS-CF model system that was mentioned and its use for air quality forecasting, including some methods for bias correction to get localized forecasts. I'm going to be talking about a lot of materials today, and if you want to learn more or go more in depth about some of these topics, I have a few recommendations. The first is the Applied Remote Sensing Training Program, or RSET, at NASA. This is a program which offers free trainings, courses in how to access and use satellite data for various applications, including health and air quality. These trainings are either in person or online. The online trainings are recorded, and you can go back and watch past trainings from our website. The trainings are mostly in English, but some trainings are also provided in Spanish as well. The next resource I want to point out was the Health and Air Quality Applied Science Team at NASA, or HACAST. These are groups of NASA and university researchers who partner with air quality application specialists in the US and around the world to apply NASA data to address health and air quality problems. And if you go to the website, you can look at examples of current, ongoing, and past projects to get some ideas of different applications that have been done, as well as they also have a guide to how to get started and find appropriate data sets for your particular application. So with that, a little bit of a high-level overview of what NASA's role is in terms of air quality. So it sometimes gets overlooked, but in addition to exploring space, NASA has the mission of observing the Earth from space and from the air. And so many of the satellites operated by NASA, shown in the slide here, as well as satellites from other space agencies around the world, have either a primary or a major secondary function of observing the state and the composition of the Earth's atmosphere, which has important applications in terms of air quality as well. And that's what I'm going to be focusing on today, and talking about some of the satellites and missions that I've highlighted here, which provide relevant data. And in the second part of the presentation, as I mentioned, my colleague, Dr. Emma Knowland, will be talking about the other important information source we have, which is models of the Earth, including models of the Earth's atmosphere, which provide a context for interpreting some of these satellite observations, as well as some other detailed information about the state of the Earth's atmosphere, including parameters which are relevant for air quality. So to get started, I wanted to give a little bit of an overview of some basic concepts of satellite data. So the basic idea behind the way in which satellites observe the atmosphere, at least as it relates to air quality, is that typically we take the sunlight, which passes from the sun through the Earth's atmosphere, reflects off the Earth's surface, passes back through the Earth's atmosphere. Along the way, it's interacting with particles and gases in the atmosphere, which is changing its properties in terms of its frequency and intensity of wavelengths of light at different frequencies. And that data is then collected by instruments on satellites orbiting the Earth. And using that spectral information together with retrieval algorithms, which are mathematical models of the underlying physics and optical properties of these different constituents of the atmosphere, we can use those retrieval algorithms to extract what we call geophysical quantities, basically properties of which are relevant to the Earth and its system, including the atmosphere. A couple of key geophysical properties that we care about in terms of air quality, which I'll be discussing in this presentation, are aerosol optical depth, sometimes also called aerosol optical thickness, AOD or AOT, which is a measure of the total scattering and absorption of usually visible light in the atmosphere due to the presence of particles and droplets or aerosols. Another important characteristic is we can use the properties of different gases in terms of how they interact with and absorb and re-emit radiation to derive the spectral fingerprints of different gases. And using retrieval algorithms, we can extract information about the presence and the concentration of these trace gases in the atmospheric column based on the attenuation of the solar spectrum by these gases. So that's the basic principle by which most of the data I'm going to be talking about today gets collected. So the characteristics of satellites really affect the kinds of information they can collect. So a couple of key characteristics I want to talk about. First is the orbits. So the orbit really determines what the satellite can observe and when it can make observations. And typically, the satellites that I'm going to be talking about today fall into one of two different types of orbits. First, on the left, we have polar orbits, which pass sort of north to south and south to north over the Earth's poles. And as they do that, the Earth is rotating underneath them, which means that over the course of typically about 1 or 2 days, they will trace out a path which covers all, or at least most, of the Earth's surface and ability to observe most of the Earth's surface. These are also typically synchronized with the sun, such that these overpasses are happening at roughly the same local time of day, according to the position of the sun, at each location. So you're getting one observation on average per day at roughly the same local time of day. This contrasts with geostationary orbits on the right. These are farther out and they're synchronized with the rotation of the Earth, such that the satellite is always observing the same hemisphere of the Earth, or the same parts of the Earth. This allows the satellite to make more observations during the course of the day, but with the limitation that it's always restricted to observing the same parts of the Earth all the time. It's not observing the full Earth's surface. So, types really determine the kinds of information in terms of the temporal resolution and the spatial coverage that the satellites provide. So in addition to that, there's also the spectral characteristics of the instruments, and these really determine what kind of information can be extracted from the electromagnetic spectra information. And typically for air quality, we classify these, or we group these into two groups. The first is multispectral instruments, which have a lower spectral resolution, a coarser spectral resolution. These are typically more suited for aerosol observations. So I have an example on the spectrum here. The MODIS instrument, you see those orange bands highlighting a couple of the key spectral bands of MODIS. Those bands are between 10 and 50 nanometers wide, so fairly coarse resolution. This contrasts with hyperspectral instruments, something like TRPOMI, which has a bandwidth of about half a nanometer. And that higher spectral resolution really allows for disentangling the signals of different trace gases in the atmosphere, so providing more information which is relevant for the presence and the concentration of gases in the atmosphere. So another key property is the spatial resolution, basically the resolution of the pixels in the satellite-derived images, which allows to distinguish spatial differences in concentration. And I'm showing some examples from those hyperspectral instruments on the previous slide, what their pixels look like mapped onto the surface of the Earth. And as we go from some of the older instruments, GOM2, Skiamaki, OMI in the early 2000s, to the more modern instruments, TRPOMI in the blue there, and TEMPO, which just recently launched in the pink, you can see the general trend is towards improved spatial resolution of these data. This means like that for OMI, for example, we were able to distinguish sort of urban versus more rural areas. With something like TRPOMI, we're now able to pick out some of the differences over urban areas and even pick out individual major emission sources like big power plants and major highways and things like that. So that improved spatial resolution has improved our ability to pick out some of the fine features and differences which are relevant for air quality. Overall, what are the major advantages of using satellites for air quality applications? And I think there are two key ones to highlight. The first is the wide area spatial coverage, covering either major regions of the world or even the whole world for the case of polar orbiting satellites, which give us this high-level overview of the pollution situation regionally. You can see an example of that for the Indian subcontinent, where here we can pick out cities, and even individual power plants are showing up here, as well as the transportation of pollution due to the prevailing wind directions and accumulation in valleys and river basins and things like that. So really giving this high-level overview of the air quality, the situation which is potentially relevant for air quality. Another advantage, many of these instruments have been operating for years, in some cases decades, where it's the same instrument in the similar orbits passing over given locations very systematically. So from that, we're able to create these trend analyses. I have an example here for Mexico City using the OMI data record back to 2005. And over that time period, so the total column NO2 over Mexico City has decreased by about 40%. So this is an example of the kind of trend analysis you can do with this long-term data record from satellites. We also have to acknowledge some limitations of satellites for air quality. I mentioned earlier, these satellites mainly rely on sunlight to make their observations, which means at nighttime they won't be able to make observations, and through dense cloud cover or even dense smoke cover, observations are usually obscured, which is of course important for certain air quality applications. Also, these satellites are measuring the conditions throughout the entire column of the atmosphere, from the surface up to where the satellite's orbiting. And those column quantities, like aerosol optical depth, may or may not be well related to what's actually happening at the surface level where people are living, and which is most relevant for air quality applications. So, for example, translating between aerosol optical depth, which is a column quantity, and surface level PM 2.5 mass concentration, for example, which is a surface level quantity related to aerosols, is not necessarily straightforward activity. I'll talk a little bit more about that later. And finally, this is more of an issue for polar orbiting satellites, where the overpass times would restrict our understanding to only certain times of the day when the satellite's overhead. This is a little bit less of an issue for geostationary satellites, which are providing multiple observations, but they're still only observing during the daytime. So we have to be careful about biasing our understanding only towards what the satellite's directly observing. With sort of a general overview, I want to recap some of the terms. A lot of these I've talked about already, but these are sort of key terms for satellite data. The first, sort of distinguishing the satellite, which is the spacecraft, from the instrument, which is the actual instrument collecting the data. Sometimes these terms are used interchangeably, but that's the distinction between satellite and instrument. Swath, or field of regard, refers to what the satellite's actually viewing. So for a polar orbiting instrument, that would be sort of the width of the data field that's being mapped out as the satellite passes overhead. Whereas field of regard, typically for geostationary satellites, refers to what part of the Earth the instrument is looking at. Overpass time, equator crossing time, relevant for polar orbits. So when is the satellite coming overhead for a given location or for the equator? Ascending, descending refers to whether the satellite's on a south to north or a north to south part of its orbit. Temporal resolution, return period, I talked about in the context of the orbits, how those affect how often the measurements can be made. The spatial resolution I talked about, it's sometimes important to distinguish between the nadir resolution, which is the resolution of pixels directly below the instrument where the satellite's orbiting, versus the edge resolution, when the satellite's looking towards the edge of its swath or the edge of the field of regard. It's looking at an angle, so the resolution will be lower towards the edge. Spectral resolution, I mentioned why that's important for measuring either aerosols, or with higher spectral resolution, you can get information about gases. Data product refers generally to the outputs of retrieval algorithms in terms of the data they provide. Granules is sometimes used to refer to generally the files in which these data are stored and provided to users. Quality flags. So in addition to the retrieval algorithms run, they also produce information on the quality of the output based on the quality of the inputs they were using and whether they were able to even run completely. And sometimes it's important to filter data based on quality. For example, was cloud cover interfering? We may want to filter out pixels that were flagged as being too cloudy to get an adequate retrieval. I talked about column concentrations and aerosol optical depth and the differences between those column quantities and surface quantities. And then finally, I wanted to spend the next couple slides talking about processing levels. So we use these levels to describe the amount of analysis that has gone on to creating different data sets. So we start from level 0, which is the raw information that's coming from the satellite. And then at level 1, we combine that with information on the position of the satellite, where the instrument was pointing, to provide georeferences to the raw data. So typically level 0 and level 1, not very useful for air quality applications. Next slide, please. In level 2, we start to get useful information by applying the retrieval algorithms to extract, for example, in the figure here, the column concentration of NO2 from the data. So we start to get information which is more relevant for air quality applications. At level 2, the data is still at the native or the raw resolution of the satellite. So this is the highest resolution information we have. And typically, this is also a range of different qualities in the data. So the quality flags have been generated, but the data has not necessarily been filtered for quality control. So you have a little bit more control in terms of whether you want to allow or disallow different levels of data quality in your analysis at level 2. We also sometimes go to level 3. And at level 3, we take the sort of the native resolution information and we remap it and regrid it to create a uniform data set with uniform grid spacing in space and in time. This makes the data typically much easier to work with because it's on this uniform grid. As part of the gridding process, we also typically apply those quality controls. So we're only using the highest quality information to create these gridded data products. And for those reasons, we generally recommend certainly new users who are new to satellite data, to start with the level 3 data products because they're the easiest to work with. Whereas the downside here is because they're being regridded, they're a bit lower resolution than the level 2 products typically. And then finally, if we go to level 4 products, this is where we bring in multiple information sources. So this can be data from multiple satellites, or more commonly, a merger of satellite data with model information to fill in some of those gaps. And that's what my colleague, Dr. Emma Knowland, will talk about in the next section. I want to focus on 2 instruments here. These are the most commonly used. The first, MODIS, the Moderate Resolution Imaging Spectroradiometer. This instrument operates on 2 satellites, Aqua and Terra, launched in the late 90s, early 2000s. These are polar orbiting satellites, so between them, they provide coverage of the Earth between 1 and 2 days, every 1 and 2 days, depending on where exactly you are. And the overpasses are synchronized, where Aqua is orbiting with an overpass in the late afternoon, about 1:30 p.m. Terra passing overhead in the late morning, about 10:30 a.m. These are multispectral instruments, so more suited for aerosol observation. More recently, VIIRS, the Visible Infrared Imaging Radiometer Suite, has been launched. It's currently operating satellites with the same instrument. Also a multispectral instrument providing aerosol information. Also overpasses typically. These instruments are providing, in addition to the true color imagery, they provide aerosol optical depth, various aerosol optical depth products related to the aerosol optical depth, as well as fire detections, so detections of fires. And then VIIRS also provides smoke and dust detection and index products, which I'll talk about a little bit later. So starting off with aerosol optical depth, this is a sort of a side-by-side comparison of MODIS on the left with VIIRS on the right. You can see the aerosol optical depth here is the yellow shaded colors, so yellow being a lower and red being higher aerosol optical depth. This is from the same day. You can see broad similarities in terms of the aerosol optical depth. You can see the gaps in the aerosol optical depth retrievals due to the presence of clouds and of snow cover on the ground. There are also gaps over the oceans due to sun glint, those sort of horizontal, vertical slanted oval bands. In addition, with the MODIS instrument, its narrower swath width means it's not covering the full Earth's surface in one orbit. It would need 2 orbits to fully cover that. So you see those sort of black, sort of cigar-shaped gaps in between some of the orbital paths. So it's a general comparison of the 2 instruments and the advantages of VIIRS in terms of the spatial coverage of the newer instrument. There are also multiple retrieval algorithms which are applied to the data from these satellites to extract the aerosol optical depth information. And Without going into too much detail, just a brief overview. There's the deep blue and the dark target algorithms are commonly used. They provide different data products at the 10 and at the 3 kilometer resolution scales approximately. Deep blue only provides aerosol optical depth information over land surfaces, and it's most useful over bright surfaces like deserts. Whereas the dark target algorithm provides both land and ocean retrievals, and it tends to operate a little bit better over the dark surfaces like vegetation, for example. And then finally, very commonly used for air quality applications is the MIAC high resolution data product that provides a 1 kilometer data product by combining information from both the MODIS Aqua and MODIS Terra instruments together. Currently, this algorithm is only applied and only applicable to the MODIS data. There are efforts under the way to update this and apply it to VIIRS data in the future, which we'll hopefully have access to soon. But for now, it's only a MODIS only product. So you can see by comparing these some differences, both due to the increasing resolution and due to the different retrieval algorithms in terms of what the actual aerosol optical depth information is being extracted from the raw satellite data. And that can make some differences in terms of which products you're using for your application. In addition to that, there's fire detection, which I mentioned, basically detection of large thermal anomalies, which are in most cases due to the presence of fires. In addition to the anomaly, there's also the radiative power and the energy emitted by those fires. There are estimates of those quantities, which are related to the intensity of the fires. Next slide, please. And then for VIIRS, it also provides a dust index and a smoke index, which are visualized on the map here. You can see in the yellow and orange colors, the higher dust index over the deserts, and then as the Saharan dust is being blown out across the Atlantic Ocean. And then due to some fires in Central Africa, you can see in the pink colors those smoke aerosol index detections. So a little bit of an indication of the probable sources of different types of aerosols from this VIIRS data product. So I've talked about MODIS and VIIRS as being polar orbiting instruments. There are also geostationary orbit instruments which provide aerosol optical depth information. One of which I want to mention here is the GEOS-East instrument. This is operated by the National Oceanic and Atmospheric Administration of the US. It's called GEOS-East because it's over the US East Coast, but of course it covers most of the hemisphere as well in its field of regard. You can see those the colors in the map here. So important to note, with a geostationary instrument, you're getting more observations per day. In the case of GEOS-East, there's about one full disk image like this taken every 10 minutes. So you can use that to get some information about some of the more rapid changes in aerosol optical depth than would be possible with the MODIS or the VIIRS polar orbiting instruments. Next slide, please. And finally, I alluded to this earlier, but just to talk about it in more detail, relating aerosol optical depth to surface level information, for example, PM 2.5, often requires different information sources. So this is an example of a satellite-derived surface PM 2.5 data product from the Van Dongeler et al. Research group. You can see the citation at the bottom of the slide there. And they combine data from the satellites for the aerosol optical depth together with model information and surface-based measurements where those are available to create this kind of a derived surface level PM 2.5 estimate product. In this case, it's an annual average. I think more recently, they're also putting out monthly average data products. But this is an example of sort of the process. You can read this paper to read about some of the processes that are involved in going from the aerosol optical depth, which is the column quantity from the satellite, to the surface level quantity, which is PM 2.5. And I also finally want to highlight an upcoming mission. This is Maya, the multi-angle imager for aerosols. Unfortunately, you can't see the animation in the static slideshow, but basically this is a little bit different from the earlier instruments I measured in that as it passes over a given location, the angle of the instrument will actually change so that it will look at the same region of the Earth's surface from multiple different angles as the satellite moves overhead. And this will be done for many target areas around the world, which are shown on the map here. And by looking at these locations from multiple angles, we're able to derive information on the vertical distribution of the aerosols in the atmosphere, as well as the size profiles of the particles, and a little bit of information about the composition as well, rather than just the simple aerosol optical depth measurement provided by these other satellites, which I've been discussing. Furthermore, in addition to just the satellite mission, this is going to be closely coordinated with surface monitoring campaigns in a lot of these target cities, as well as health studies to try to connect the aerosol composition information from the satellites to the health impacts that those are having. So this is going to be hopefully a very useful mission for really understanding those aerosols and their health impacts around the world. And hopefully it will be launching next year. Again, I want to focus on two of the hyperspectral instruments now. First, the OMI instrument, the ozone monitoring instrument, is on the Aura satellite, launched in the early 2000s. As I said, this is a hyperspectral instrument. It's in a polar orbit. So it's passing overhead every day at roughly 1:45 p.m. local time. And the spatial resolution was about 13 by 24 kilometer pixel sizes at the nadir, as you saw on the slide a little bit earlier. More recently, TROPOMI, the tropospheric monitoring instrument, was launched on the Sentinel-5 satellite, or Sentinel-5P satellite, in 2017. It's important to note this is not a NASA mission. This is actually a European Space Agency mission. But through an agreement between NASA and the European Space Agency, we're actually able to share the data from this satellite mission as well on our NASA system, so making it a little bit easier for people to access data from multiple satellites of the same platform, even if they're operated by different agencies. Also a hyperspectral instrument, also in a polar orbit with a roughly 1:30 in the afternoon local overpass time. Major difference here being the improved spatial resolution. You can see for some of the bands going up to about 3.5 by 5.5 kilometer nadir resolution. So improved spatial resolution being the key difference here. Next slide, please. Both satellites provide data products related to the tropospheric and total column NO2 concentrations, as well as sulfur dioxide, formaldehyde, and ozone information as well, although there are some caveats to that, which I'll talk about. TROPOMI, because of its wider spectral range, also can provide information on the carbon monoxide and methane concentrations as well. So the reason I mentioned those caveats for ozone was, because of the ozone layer, basically the higher concentrations of ozone higher up in the atmosphere really tend to mask the surface level ozone concentrations, which makes it much more difficult to determine the near surface ozone from satellite data. And for that reason, we typically recommend against using satellite-based ozone data for air quality applications, just because it's so difficult to distinguish between the near surface and the upper atmosphere ozone. There are some exceptions to that, which I'll talk about later, but this is the general recommendation for ozone. On the other hand, nitrogen dioxide, because of its short lifetime, tends to be really concentrated near the surface. So what we see from the satellite tends to be fairly well related to what's actually happening at the ground level, which makes it very useful to use satellite-derived nitrogen dioxide for air quality applications. I mentioned both OMI and TROPOMI provide NO2 data products. OMI has been in operation longer, so if you're looking at a long-term trend analysis, that would be the better instrument to use. TROPOMI, with its higher resolution, was launched more recently, so that would be better if you're looking at some fine spatial distinctions between NO2 in different areas. Formaldehyde is also important, and its major use as it relates to air quality is to take the formaldehyde retrievals from satellites and use those together with the NO2 retrievals from satellites, where the formaldehyde acts as sort of a proxy for overall volatile organic concentrations, VOCs, and the NO2 data product acts as sort of a proxy for NOx. And by taking the ratio of those two, you can make some determinations about the ozone formation potential, whether you're in a VOC limited or a NOx limited regime for ozone formation. So that's really the most common application of this formaldehyde product to air quality applications. I have an example on the slide here of that over the United States. Next slide, please. The sulfur dioxide from satellites, we're mainly seeing the major emitters, those being volcanoes, as well as certain large power plants and certain industrial operations like smelting really show up in the satellite data for SO2. And again, both OMI and TROPOMI are providing those satellite data products for SO2. And finally, I briefly mentioned carbon monoxide and methane data from TROPOMI. Carbon monoxide is useful because of its longer lifetime. It makes it a useful tracer for different kinds of combustion activities or pollution activities. And then methane, being a potent greenhouse gas, is also important to monitor both the major point sources, mainly natural gas operations, as well as distributed sources of methane like agriculture sources. And again, Tropomi provides data products for both of these as well. So in addition to just the measuring the column concentrations, we can again apply some creative algorithms to this to get at a little bit of the surface emissions of these different pollutants. These typically operate better when there's a sort of an isolated point source surrounded by a cleaner background area where you can really distinguish between what's being emitted from the individual sources. And I'm showing an example here of how this has been done for sulfur dioxide around the world, picking out some major point sources and categorizing them into different types, as shown in the map here. So this is useful for creating what's called top-down emission inventories from satellite data, which have some advantages over the traditional bottom-up approach to creating emission inventories. They can be a little bit easier to do and be a little bit less time-consuming, and they can also a little bit better keep pace with changing emissions and also detect some emission sources that might have been missed by the bottom-up inventories. So that's another useful application for satellite data for trace gases. And then finally, unfortunately, again, the animation's not running for this one, but I want to highlight the TEMPO mission, the Tropospheric Emissions Monitoring Pollution Instrument. This was actually launched in April of this year. It's currently undergoing checkouts, and hopefully we'll be getting some data from it early next year. But this is a geostationary mission for trace gas monitoring over North America. So it's going to provide hourly retrievals of some key pollutants, NO2, formaldehyde, and also a near-surface ozone retrieval. I mentioned earlier how difficult that was, but they're going to use some new algorithms and approaches to extract that information and hopefully give us some relevant near-surface ozone products. This is a geostationary mission, as I mentioned, providing hourly data. The field of regard covers North America, so it includes, towards the bottom of the field of regard, it'll include parts of Mexico and the Caribbean as well. So there'll be some useful information, I think, for Mexico City as well coming out of this mission. So again, that's another mission we're really looking forward to in the coming year. And there's a couple of websites I want to highlight here. You may already be familiar with them, but in case you're not, the first is NASA Worldview. So this is a website you can go to, and the main purpose of this is to visualize satellite data, especially near real-time data. So the data that's available within a certain limited amount of time from when it's collected. There's some fast retrieval algorithms which can be applied to get that data available to the public quickly. So using this user interface on the website, you can pan, you can zoom into different areas, you can move backwards and forwards in time using the slider at the bottom, and you can bring up different layers and overlay them onto the image to visualize different satellite data products. So next slide, please. I just have an example of this where I kind of zoomed into northern Mexico, southern US, and I'm overlaying on the true color image in the background, I'm overlaying the MIAC AOD product in the blue shaded colors, as well as the VIIRS fire detection product in the red dots. And you can see, for some of those red dot fires that are being detected, you can very clearly see the increased aerosol optical depth in the plumes coming off of some of those fires. So just this Worldview is basically a quick tool for making these kinds of easy visualizations of the satellite data. If you want to do more in-depth analysis, there's the Earth Data Search, which it looks kind of similar to Worldview, but the main function here is to find the relevant satellite data granules that cover your region of interest and download them to analyze on your own. So you can use this interface here to select different data products using those menus on the left-hand side, and also create spatial bounding boxes and bounding regions to limit your data search. Also limit your data search temporally to certain dates or certain times. And then the website will execute that search and return to you a list of the data granules that satisfy your search criteria with some instructions on how to download them. And you would then download them and do some analysis on your own. And again, the RSET trainings provide some details about how to analyze data, some of these data products, once you've downloaded the data. Next slide, please. To avoid downloading the data, there is a tool called Giovanni, a website called Giovanni, which I'm showing here. The key advantage of this is you can perform some simple analyses online without having to download all the data and analyze it yourself. And so what this interface does, again, is let you select different satellite data products. In this case, the limitation of Giovanni is you're limited to the level 3 and the level 4 data products. That is the gridded data. You can't work with the level 2, the raw native resolution data products, at least not yet. But if you're looking at these level 3, level 4 data products, you can bring them up. You can choose a region of interest, a time interval of interest, and you can select a couple of different analysis and plot types in the upper left corner. And just to show a couple of examples of that, this was an analysis I did where I selected a region covering Mexico, and I told it to get me the level 3 NO2 data product from the OMI instrument covering that region for the year of 2022 and create a map of the average of that. So that's just what it spit out here. And you can see some of the major urban areas showing up in that data product: Los Angeles, Mexico City, and a couple of other urban areas. So that's just an example of kind of a simple visualization you can create without having to download and analyze the data yourself. Next slide, please. This is a little bit more of a sophisticated map, but just to show you the flexibility of the tool. This is now a correlation map, and what it's showing is the correlation between the MODIS aerosol optical depth data product over the course of 2022, the correlation between the aqua MODIS and the terra MODIS, that is sort of the afternoon overpass versus the morning overpass. So the idea here is if those are more correlated, then the aerosol optical depth tends to be more consistent throughout the day, whereas when those are less correlated, the aerosol optical depth may be more variable throughout the day, which might indicate more variable PM concentrations throughout the day. So you can see on the map, so most of these areas in the darker blue colors, most of these areas have a good correlation, but there are some areas, northern central Mexico and Baja, where the correlation is poor, which might indicate more variability in aerosols during the day. So another example of the kind of analysis you can do with the Giovanni tool. That brings me to the end of my section. I want to reiterate, I presented a lot of information. Again, there's the Applied Remote Sensing Training Program, RSET, on this slide. There's also HACAST, the Health and Air Quality Applied Science team. These are good resources to learn a little bit more about how to do some of the things I've talked about here in practice. So I'd recommend you look at those if you're interested in learning more. Thank you very much.
We have 10 minutes for questions and answers. ¿Sobreponen las capas de formaldehído o hacen la operación directa de formaldehído entre NO2 satelital para sacar este mapa?
This is not something I'm directly familiar with. I refer you to the paper cited on the slide here. But in general, yes, you can sort of just take the ratio of the formaldehyde data products and the NO2 data products from the same satellite. You may actually be able to do this in the Giovanni system. I'm not sure, but you are able to compare two data sets, and you may be able to, I think, take the ratio of the two data sets directly in Giovanni. If not, you'd have to sort of download the data and make the ratios using just a computer program. But I think there are some caveats to that. The paper goes into a lot of detail about this, but there are some quality control steps that should be applied to both the NOx and the formaldehyde data. And because you're taking the ratio with NOx being the bottom of that ratio, at very low NO2 concentrations, it wouldn't be very reliable. You'd get unrealistically high ratios. So this is more useful in areas where the NO2 is not very low. You could kind of see that on the map here. Some of the more rural areas and then over the ocean, the ratio is very high, getting up to about 8. That may be a little bit unreliable. But in the more urban areas with the higher NO2, the ratio tended to be, at least according to the results in this paper, a little bit more reliable. And this is, in this paper, I think I don't know if they do this analysis globally. They certainly do it for the US, as they show here. I don't recall, but you can read the paper to find out whether they've done this already and they might provide the data products. If not, as I mentioned, I don't know off the top of my head, but Giovanni may be able to do this for the OMI data set, which is a level 3 data set.
Thank you, Carl. One question about the trends you show in one of the papers, I guess it's Gupta et al., about the trends of NO2 over the time, which is very useful for evaluating not only the trends, of course, exposure, but maybe could be used by the cities to know what has been the impact of certain interventions. But my question here is that graph itself is very useful, right? I mean, to do that trend. So how is that type of analysis being generated? Is that a request? Is just something that some researchers want to ask about? How can we reduce that, or how can we engage more the questions that the end users, in this case, it could be Mexico City, or any other city who is represented here, to have that type of analysis? Because you mentioned we can download the data, we can do some analysis, but we also know that it requires a lot of QA/QC, as you were mentioning, using level 3 data. And but at the end, I think that's also part of the idea of generating these products, right? That users, like in this case, authorities from the cities, air quality practitioners who are already working in the cities, could have that type of analysis. So I don't know if you could just comment about.
Yes. Once you have access to the slides, if you go to the very bottom right corner, you see it says NASA GEOS-CF nitrogen dioxide trends for world cities. You can click on that link, and these plots have been pre-generated there for many cities around the world. And I looked for Mexico City, and they had this plot already there. So that's one, that's one option, is to just check there. So for NO2 specifically, they have those plots. Another option, I believe these plots may have been generated with the Giovanni tool that I showed. So in my examples, I only showed maps, but one of the options in Giovanni is to do a time series plot. So if you picked, for example, the OMI NO2 data product, which is what's being used here on that Giovanni list, you gave it the time interval from late 2004 or 2005 to, let's say, the present. And you picked in the upper left-hand corner, one of the options is an area average time series plot. And you would draw then a box. There's an option where you can draw a box on the map. You draw a box around your area of interest, in this case, maybe Mexico City. And you would click to generate the plot. And it would create a plot very much like this, where it would be the time series of the observations for your region of interest specifically that you pick out on the map. So that's where certain analyses, including this kind of a time series analysis, can be done in Giovanni with the level 3 data. So the quality controls have already been applied, and it's already been, I think there's a monthly average data product. So it's already the monthly average has been computed, which is what's being plotted here. And then it would just average over your area of interest and create this plot for you. So I think if you go to the Giovanni website, there are some tutorials. If you go to the help option, there's some tutorials about the different kinds of plots. But if you just kind of explore the tool and see what's available, there are certain analyses that you can do where a lot of the work is kind of being done for you, where you don't have to download the data yourself and do this analysis. I mentioned earlier, for the formaldehyde to NO2 ratios, I'm not familiar, but it may be possible to do those within Giovanni. But there are certain limitations to the kinds of analysis you can do in Giovanni. So my recommendation, I guess, would be to try to do it within Giovanni. That's typically easiest. And if you run into problems, that's where the next steps would be, for example, to reach out to the HeyCast team, which I mentioned. There's a user forum in HeyCast, so you can post questions in that forum about, if you're not able to do something, you could explain, I tried to do it in Giovanni, but it wasn't able to do it. They may be able to help you there. And, potentially if it's something that a lot of people are interested in, it might become a topic that HeyCast picks up in the future to actually develop dedicated tools. So I think a lot of these, I'm not familiar, maybe not Giovanni, but a lot of the sort of the user-friendly tools were developed as a result of projects like HeyCast. identifying needs of end users, and then building the tools to meet those needs.
Thank you, Carl.
So the whole idea was to have this in-person training. We have been working on this first with you. We call this CTAQ, and then we evolved to the CanAIRy Alert and trying to include other tools. So the whole idea is recognizing that there are so many tools and data and development that the scientific community has been developing over the years that are out there in terms of that could be of help for the air quality practitioners in cities, but also the recognition of that that even though those tools, this data is there, air quality practitioners in cities not always know about them, or they don't have the time to use it right away. So that was the whole thing of these data and tools from WRI point of view. Can we make that bridge between the scientific community, the developers, and the users, and also knowing what are the needs from the city's perspective? Knowing that they are very dedicated people. They have, some of them have a lot of years of experience, but they are usually overloaded. They have many tasks within their agenda. And even if they want to get trained, sometimes they don't have the time. So this idea of the community practice was also to, to identify what could be the tools and the needs so we can make that time even shorter and just be very directed. So this is what we have been trying with you guys, also with Dr. Benjamin Defoe, with Dr. Michelle Grutter. What do they have? And then how can the cities from there, air quality practitioners from the city can use. So over the last 2 days, we first have a day, and we will share with you, of course, presentations from each of the participants, telling us what are their needs, what are their challenges, but also what they have been doing on air quality using data and tools in order to identify what could be those offerings that maybe teams like yours could be offering to them, or at least, as you mentioned, Carl, well, it's there. So just click on it and check and ask for it. So that's a great thing. And particularly in the air quality forecast, the bias corrected. As you know, we have a cohort of cities, 10 cities that participate in the CTAQ. 3 of them are actually here, Bogota with Edison, and Monterrey Metro with Gerardo. And they are our assets. We always make a lot of noise because they have been using the bias corrected air quality forecast since it was started, and they can very briefly tell you the differences, right? Gerardo just shared with us that the governor is asking the air quality team every week to update him based on what is the air quality forecast is saying. And we have also heard from other technical sessions that Bogota is finding now that their quality forecast is not, the performance is not as good as it used to be, and I let you talk. And also the Monterrey. Why? Because after the pandemic, and in the case of Monterrey, the data that we used to train them, to generate the bias corrected, was not as good 3 years ago as the one that they have now. They have a new air quality network. They have been working a lot with the quality assurance, quality control. So they have better data. So that's a very good case. In the case of Mexico City, even though that they have been part of the CTAQ and then CanAIRy Alert, they have been telling us since a long time that they would love to have a bias corrected air quality forecast from GEOS-CF because they can have it as a part of the ensemble. So that's so far like a very summary that this is the opportunity. We have Kampala here represented by Alex, and we want to convince him that he can use their quality forecast that is ready to be there, because Christine and Christoph and Carl have been working on that, or generating this bias corrected forecast. It was a challenge because we were going to use data from local sensors in these 4 cities. And we found a lot of challenges with the data, similar to the ones that we found when we were using reference data. And we have also Mrs. Ramawati here from Jakarta. And we would like to use this opportunity for her to know what is this bias corrected air quality forecast, because even though that we have been generating the air quality bias corrected forecast for the 2 monitoring stations from the embassy in Jakarta, we haven't been able to share with them and at least see how they can use it. So this is a very precious opportunity, because here we have the cities, we have Jalisco, we have Nuevo León, Mexico City, Bogota, we have Kampala, we have the team WRI Indonesia, and also we have Jakarta, Mexico City, and Querétaro, who is also having Querétaro State. They have also a very new and very well QA/QC data from the monitoring station. So you see, that's the opportunity. So we want to take this opportunity just to say, well, those who knows very well what their quality bias corrected forecasts are, they have specific requirements and probably wish list, as Monterrey and Bogota, and others who maybe just we can encourage them to use the forecast. So that was the whole idea. We will share with you all the presentations. We have some recordings, so that's and thank you so much for being with us. We wish we could have you here in one of the chairs, but we hope that we could have that opportunity very soon. So that was kind of the very brief, and I think I'm taking more time. And maybe during the questions, Edison and Gerardo, you can also share what have been your experience using the GEOS-CF bias correct forecast. We will continue maybe in the session.
Thank you so much for that round the room introduction. It's so great to see everybody here, and Carl and I and Christoph wish that we could be there with you, but all three of us are currently traveling home visiting family, whereas Christoph's is much further away. I'm actually based here up in Maine in the Northeast, so I'm far from those, I think, and Carl's not too far, also in New England right now. So we are a bit far from Mexico, but hopefully the connections are good that we've been able to see our presentations and get a lot out of it. The presentation I'm going to share today is not only on the GEOS-CF, I'm going to give a little bit of a lead up to the GEOS-CF. So going over different forecasting capabilities from the Global Modeling and Assimilation Office. The slides have been a work of progress from myself, as well as Drs. Christoph Keller and Carl Malings, who you now, at least now Carl and myself, and hopefully through other interactions, you know Christoph also quite well, as well as several other scientists from NASA Goddard Space Flight Center. So NASA Goddard is based just outside Washington, D.C. And so in the hour that I have, I'm going to give an overview of the GEOS model. I'm going to show you some additional ways that you can access our big data, because it's a global model, so it's a lot of information. And then I'm going to show you the bias correction techniques that we're developing in our office. And so Carl, I think, did a really nice job of showing you why NASA. Like, we're observing Earth from space. We've got a lot of information. And so our office, GMAO, really tries to synthesize that information using our Earth system model to really understand and be able to predict the changes in the Earth system. And we do this with our Earth system model, GEOS, which stands for the Goddard Earth Observing System. So as the name says, it's mainly designed to advance the use of satellite data products. And Carl's already shown you how we can get different information about things like ozone, carbon monoxide, AOD from space, both in the column, as well as some profile information. And so we use this in our models through a method that's called data assimilation, so a process which combines and propagates that information of the observations both in space and time, using mathematical equations and statistical error estimates within the model. And so we can run it in many different configurations, but we do run it like a weather forecasting model. So we can do, we do 5 to 10 day forecasts with our state of the science GEOS-FP model. So we haven't talked about that one yet, but this one gets updated roughly every 6 to 12 months. And this way we're able to take in new observations that come online, as well as constantly upgrading the GEOS model to be that state of the science. And what we can do is take a version of that model and we can reanalyze past observations in order to have a data product that can be used for trend analyses. And so MERIT-2 was our latest reanalysis when I joined NASA Goddard back in 2015. And we're actually in the final stages of our next reanalysis, so that's quite exciting. And both GEOS-FP and MERIT-2 have a simple aerosol module. So this one is showing the fire radiative power from satellite that Carl introduced in the previous slide deck. Over South America, you can see those red dots. That's the information of fires coming from satellite. And then in our model, we can actually derive information about the aerosol. So you can see orange is dust coming across the Atlantic from Africa. You can actually see in the Southern Ocean that blue swirls are sea salt being wrapped up in a weather system. And then coming from the fires, hopefully you can see my cursor here, there's a bit of a green color, and that's actually the organic carbon and black carbon from those biomass burning regions. And then you can kind of see a little bit in some of these urban areas, the white, those are the sulfates coming from industry. And so we wanted to go a step further, right? So we want to actually be able to estimate tropospheric and stratospheric chemistry. And so we couple the GEOS model with the state of the science GEOS-Chem chemistry module. It is very sophisticated. It's got 250 chemical species and over 700 reactions in the version we've been running since like 2017, 2018. And so this way we can combine all this information to get both aerosols and chemistry together. And so what I've shown in this image here is just the high resolution information of now ozone that we can get from GEOS-Chem. And so you can see even here in areas where you have very high levels of NOx. It actually eats away at the ozone. And so ozone is very low in these urban areas of China at this time of day versus very high values shown here in white over parts of North America and Europe. And so these images come from an animation that was produced at the time that we released the GEOS-CF, and it shows 96 different chemical species that directly or indirectly impact surface ozone chemistry. And this way we're able to estimate all the major air pollutants, some of the ones that, that Carl introduced earlier, not only ozone and PM2.5, but NO2, SO2, carbon monoxide, and formaldehyde, many, many others. And so how this works is because it's so computationally expensive, it uses the compute power equivalent of over 3,500 personal computers. So you have to really have access to a supercomputer like we do at NASA Goddard to be able to run a system like this globally. And so each day, usually in the early to mid-afternoon here in Washington, D.C., we start our GEOS-CF model system. And so what we do is we run the previous day over again with the weather and the chemistry coupled together in order to have the best initial conditions for when we launch that 5-day forecast. And so you'll hear me refer to that previous 24-hour period, what we call as a replay. And so we're running this at one of the highest global resolutions of a composition forecast system at what we call 25 quarter degree, or it's roughly 25 by 25 kilometer resolution. And it runs from the surface all the way up into the mesosphere. And we also not only have high spatial resolution, but we also put out some of the highest temporal resolution. So very frequent information comes from the model. You can get the surface estimates of both chemistry and meteorology every 15 minutes. But we also produce hourly both average and snapshots of the atmosphere, what we call instantaneous views of many, many species, including some of those 2D fields like the aerosol optical depth that Carl introduced earlier. And so we have been releasing this information to the public since 2018, and we actually save forecasts of the 5 most requested pollutants: ozone, NO2, PM2.5, CO, and SO2 since the beginning of January 2019. So that information can be used for research and other applications. And so similar to the ways we've made other NASA satellite data products available to the public, we really want everyone to be able to access our model forecast as well. And so GMAO has a website that we call Fluid. It's mobile friendly, which means you can look on it easily on your phone, on your tablet, as well as on your computer. And you can generate imagery of the forecasts for many different regions, like I'm showing here on this map. You can select Central America. You can see there's a wide range of regions available for the GEOS-CF. If you're savvy with computer programming languages, you can also download the data directly from our data portal, or you can access it remotely using OpenDAP server. So if you're familiar with programming languages like Python, you can also do that. We also pre-generate over 200 different images for a time series of the 5-day forecasts, which I'm showing here from yesterday's forecast for Accra in Ghana. And you can see from the tabs, you can get information for CO, NO2, ozone, PM2.5, and SO2. And it shows you what the model forecast would be for the lowest most atmosphere, as well as your surface concentrations. And for PM2.5, we have it broken down into the different speciations. So you can see the sulfate, the organic and black carbon and dust portions, as well as some of the important information for meteorology that could impact your forecast. So we have the temperature, winds, as well as precipitation. But you might be at a location that's not in one of those 200 pre-populated datagrams, as we call it. So you would be able to go to our CF_map tool, and you can click on any location, zoom in, and you can see how that grid box average from the GEOS-CF is representing your area. And then you can get the 5-day forecast. This is the example I showed a couple months ago at the WRI presentation I gave. But you can also get the historical time series. So you can go back and look at 30 days, 60 days, or even 90 days for the NO2, ozone, and PM2.5. And you can download the forecast in file formats that are not NetCDF that people are probably looking for, like Excel, JSON, or an ASCII file. So you can get the GEOS-CF that way as well. We have been working, as Beatrice said, with WRI now for several years. You can get a daily average of the forecast maps in the Resource Watch platform, but also the US CDC is now calculating the air quality index values using the GEOS-CF. And I'm showing an example of ozone on the left and PM2.5 there on the right here of the AQI on days when we knew that we had very high ozone in the Washington, DC area, which you can see here on the left-hand side. Also, in the last couple of years, we've been working through a partnership with Google to bring in GEOS products, in particular the GEOS-CF, both chemistry and meteorology fields, as well as the bunch of MERA2 fields, specifically also the aerosol fields, if you're interested, into Google Earth Engine. And so this is a great way to be able to layer the air quality information with other data sets that are in Google Earth Engine, and Carl's going to show an example of that later. But just this shows how over California, we've been able to downscale the global model to city scale using machine learning algorithms to bias correct the air quality estimate. So this is using Tropomi NO2 and the model NO2. And so it's important to note that NASA GMAO products are designed to be research products and support many different NASA activities. And these specifically measure through the full atmosphere. So the GEOS-CF is not optimized for capturing surface air quality. And so I'm going to go through some examples of showing how well we do when we evaluated the GEOS-CF and kind of showing the need to bias correct that grid box average if you want to get information at your specific location. And so we used available surface observations from different networks. The OpenAQ are the blue dots, and they're generally in more urban environments. Compared to the Global Atmospheric Watch or GAW network, which are the WDC-GG and RG measurements for carbon monoxide, ozone, NO2, and SO2. And so I'm just going to walk through these different examples, but just keep in mind that we have these rather large boxes for North America, South America here, splitting Central America between these two, as well as using the available observations that we have in places like Africa, Australia, and Asia. And so looking at model skill score against these surface observations, the top row is normalized mean bias. The middle is the normalized root mean square error, and then at the bottom is the correlation. I've put stars there for really what we're the goal, like the best value what we're trying to get at. So obviously with an error, we're trying to get as little error as possible, so as close to 0. And in the correlation coefficient, we're hoping to get as close to 1. I mean, you can see for ozone over the course of the year, so this is showing a time series for monthly skill scores, even though it's calculated based off of the daily averages. You can see that for the rural network and the triangles, we're doing a pretty good job. But when we compare to the OpenAQ sites, which represent more the urban areas, we can see that we're kind of missing some of that seasonal cycle. If we move to NO2, there are less background observations, so that might be why it's a little up and down there in the triangles, but we still see that we do a decent job, but still room for improvement. And lastly, focusing on PM 2.5 and AOD, we can see that generally GEOS-CF overestimates those aerosol concentrations, though maybe slightly better AOD at the background sites. So now looking at a map, so we can see for surface ozone, the GEOS-CF is the purple line in each one of these time series compared to the regional values in color. So we can see that in North America at these rural locations that we're picking up the springtime peak in ozone, which is often driven by stratospheric intrusion, so bringing down those high values of stratospheric ozone towards the surface. Doing quite well in some of the other regions, but you can see that in Asia we have lower values of ozone, likely due to very high NOx concentrations. And so breaking this down now, looking at the urban environments where you're probably all living and breathing, you can see here we've broken it down to the regions. I've got the map again up in the corner just to remind you of those locations. Pink is the model, black is the observations. And generally the model overestimates surface ozone in Europe, North and South America, and Australia on the order of about 5 to 10 ppb, especially in those summer months over the Americas. Whereas in contrast, the model underestimates ozone over Africa and Asia by up to 20 parts per billion. So these differences are quite large compared to what we saw in the previous slide to the rural sites, suggesting that those subgrid scale processes, those things that are happening on that local to urban scale, could really be driving some of those differences between the model and the observations. So to look at that more closely, we just focused on the afternoon observations and model comparisons. And so we can see that the bias is reduced by up to maybe 5 parts per billion, especially for Asia, South America, and Australia. And now looking at comparisons for the model bias for AOD, on the left-hand side, we see again it's highest in those European and North American sites. And what might be harder to see on your screen is that there's a dashed orange line, which is the GEOS-CF AOD, but without the sulfate aerosols. We know that there's an overproduction of SO2 emissions in GEOS-CF because of the anthropogenic emission inventory that we're using. And so here, these sulfate aerosols, they make up to 50% of the total AOD over Europe, North America, and Asia. And so if we remove that value, we get a much better agreement, except in Asia now where it's maybe bias low. So similar to the AOD comparison with the modeled PM 2.5 on the right, it overestimates in Europe, North America, and as well as Asia and South America. And so some of this SO2, in addition to the extra SO2 emissions, there could also be an overestimation of biomass burning emissions because the factors that are used from our fire emission database are designed to match the go-kart module, that aerosol module that was used in GEOS-FP and MERA2 that I showed at the start, which could lead to a bias in the CF. And so we're keeping all of these in mind as we work towards a new version of GEOS-CF, which will hopefully come out in the next, I never like to say a date, but hopefully we're spinning it up now. It's something that we're actively working on. But these are the type of things that we're hoping our machine learning bias corrections can take into consideration. So now that we've gone over what those replay portions look like, looking now at the forecast skill. And you can see that for ozone in pink, NO2 in green, and PM 2.5 there on the right-hand side, there's a little variation in the skill scores out to 5 days. Maybe a bit with the correlation come day 3, 4, and 5, it tends to drop off. And that's really because the forecasts changes are really driven by meteorology as well as persistence of any fire emission. So if it was the fires were burning today, we're going to assume it's going to be still burning tomorrow and the next day and the day after that for the entire 5-day forecast, which seems sometimes the right choice when you have something like these fires in Canada, but that's not always the case. And so that's where we can see those differences. Now, I showed this example in my presentation a couple of minutes, but I just really love it. I think it's a great example. We have these 3 monitoring stations in Leon, Mexico, and you can see here the grid boxes for GEOS-CF. And while these 3 are very close together, they're actually represented by 2 different model boxes in the GEOS-CF. And so Christoph Keller, who's unable to be here today as he's on travel, he developed this technique using the GEOS-CF. And so I'm just going to walk you through this. So I'm using the lower box with the 2 observation sites that are in the same grid box. On the right-hand side, the time series, the observations are different. So the black lines. But the pink lines are the same since it's the same model box for both. And you can see that GEOS-CF is really missing those low values that the observations have. And so we use a XGBoost algorithm to correct the original hourly average model predictions of ozone, NO2, and PM2.5 using local meteorology and atmospheric composition as predicted by the model. And so this information is, if you're interested, is detailed in Christoph's paper, and I can provide you with more information for that if you're interested. And since the model biases are often site-specific, like we could see there were differences in the observations, a separate machine learning algorithm is trained for each site. And so what we get out of the machine learning algorithm is a bias correction factor. And so it's that difference between the observation and the model. And so along with the original GEOS-CF output, we add that bias correction factor to it. We're now able to capture that diurnal variability of ozone at that subgrid scale. So you can see now the green lines are the model plus its individual machine learning bias correction factor. And so Christoph did this for all of the available sites that he could as part of our evaluation. And the diamonds in here show from the previous comparison of the original GEOS-CF, that mean values of the skill score. And now the box and whisker are for the machine learning bias corrected forecasts. And what you can see here for the normalized mean bias, again, like practically at 0 now over the course of the 5-day forecast. For the normalized root mean square error, you can still see there's maybe a slight decrease over the course of the 5 days, but drastically improved over the original model. And then for the Pearson correlation, again, we're trying to get as close to 1 as possible. And so those first few days, it really does a much, much better job, but still seeing some decrease over the course of the 5 days, likely due to things, again, like the persistence of our biomass burning emissions. And so this might be particularly of interest to those who are already using the bias-corrected forecast. So this example shows the training period for Washington, D.C., a time series of 2018 through early 2020. And this is showing the observations in black. The model is that dashed gray line, so you can see the differences between them for these locations in D.C. here. And then the red is the bias-corrected forecast. And as we went into the pandemic restrictions, the lockdowns, we started to see the machine learning algorithm no longer could predict the observations. And so we were able to estimate now the impact of these restrictions on air quality by being the difference between the business as usual, that red line, and what is observed. And so since we were doing this over now the historical portions of the GEOS-CF and not the forecast, we actually have the emissions saved from those replay periods. So we use additional inputs into the machine learning algorithms and retrained all the model for the different individual sites. Again, each one has its own algorithm. And we were then able to estimate this globally. And I highly recommend, checking out this animation if you'd like to see it in more detail. But there was over 5,000 sites that Christoph applied his machine learning technique to around the world in order to quantify those changes in NO2 from the different lockdown restrictions. And so you can see here in the time series, Wuhan, you can see that drastic decrease there in the yellow line. A little bit later for Europe, with showing Madrid in blue, and also maybe a slower decrease, but a similar timing of decrease in NO2 over New York City. And so this is just an example of how not only can we get information back from these collaborations with our end users, with the machine learning techniques. We can learn about our models, but we can also do some really interesting science with it as well. And so I'll move into a little bit more into the City AQ project, which started a few years ago, following on the collaborations that GMAO already had with WRI, which brought the daily average GEOS-CF forecasts into Resource Watch, which I showed earlier. So working with research scientists at NASA Goddard, City AQ provides that bias-corrected forecast for the first cohort of cities in Central and South America on Research Watch. So you can go to Research Watch, you can find these locations. You can find, this was an example I showed last April. And so you can see Leon, again, that example that I showed, you can now get those forecasts right there online. And then now CanAIRy, it builds upon the City AQ project. So there's a growing number of cities in the global south, as well as other cities, you know, that like we're producing this anywhere and everywhere because we have a global model. And so I understand that we're also trying to accommodate cities that have low-cost sensors, as well as not only the research grade. So for CanAIRy, I understand that first QA and QC, that quality check on the low-cost sensor data is being done before it's sent to Christoph. And we're really encouraging cities to make their data open before they join the initiative. And furthermore, WRI is developing this interface to help air quality managers interpret the air quality forecast information for decision making. So you want to understand the temporal variation, health risks, guidelines, things like that. So definitely keep in touch with WRI for more information. Right, and so what we're providing is the ability now, if you're able to upload your, well, this is something that Christoph and colleagues are working on, to actually be able to get the information via the NASA Amazon Web Service. And so this is kind of on the right-hand side is showing the Amazon AWS app, where you will be able to access the forecasts and actually be able to export the forecasts in these different file formats. And Christoph shared with me a couple of figures here, which show Bogota and Monterrey. You can see these are for a period of 2018 to 2019, which I believe is the period of time which is was used for training the model. So the observations now are shown in red, not to be confused with what we've shown before, where the observations were in black. The black is now the machine learning bias-corrected estimates for ozone on top, NO2 in the middle, and PM2.5 along the bottom. And you can see, at least in those 2-year periods, how much better represented the bias-corrected forecast would be. And so really it comes to the fact that for this to work, we're a bit of a bottleneck, in the sense that you would have to be able to provide us with your observations in order to then train the model for your location and then put it back up. And so it would be amazing if instead you're actually able to do this yourselves. And so you're actually able to upload your observations into the cloud. And so this is going to be available through the NASA cloud, interacting with this public interface. And so you'd be able to upload your data to the cloud, train the machine learning algorithm done on the cloud, and be able to get your forecast that way. So this is under development. It's very, very exciting. And so stay tuned for for more information on that from Christoph Keller and WRI. In the time I have left, I'd like to introduce you to another project that Carl and I and Christoph have been working on over the past year. And so as Carl introduced, there's different global data sources of air quality information. We have the models, as I've just shown you now, as well as the satellite data. And then we have the ground-based observations, both from the regulatory monitoring and the low-cost sensors. And they all have their pluses and minuses. And so one way of getting the most information out of these different information sources would be to combine all of the information together. And this can be very time intensive to do and likely difficult for local air quality managers to pull all of this information together for their local network. And so we've been working on a new project which aims to integrate all of this information together with the objective to design an easy to use online tool that will be on a publicly available platform, the Google Earth Engine. This way we can provide estimates and forecasts for these different cities. And we've been working with different end users. This is part of a NASA-funded applied science project that we have. And so we currently are working with UNEP, with folks in Dakar, Senegal, as well as Rio de Janeiro as our test pilots cities. And then we're also looking at a few cities across the US. And so I'm actually going to hand, in a sense, the slides over to Carl at this point to kind of walk you through what our data fusion local scale forecast would look like.
All right, thanks, Emma. As Emma was mentioning, the goal here is to combine all these data sources together in Google Earth Engines. I'm going to walk through a prototype version or some screenshots of a prototype version of the tool we're working on, which will hopefully give you a sense of how it works and how these data sources are being brought together. So this is going to be focused on the city of Dakar in Senegal, which is one of our partners who are going to be cooperating with to test out this system and develop it. So the starting point is the GEOS-CF forecast, which has been discussed. As Emma mentioned, this is a high-resolution global model, but if you zoom into the sort of the city scale, the grid boxes can be a little bit too large for that, and you can't discern some of those fine-scale differences, which is why, as Emma was discussing, you need those sort of bias corrections to correct from the model scale to the very local scale of the individual monitoring stations. But the downside is, again, as Emma mentioned, you have to do that individually for every monitoring station. And we wanted to try to do it on a little bit more of a regional scale to try to fill in some of the gaps between monitoring stations as well. So the approach here starts off with the model. That's sort of the basis. And then the next piece of information we add, next slide, please, is the satellite data. So this is now showing sort of the satellite, in this case, it's the column NO2 concentration from the same time period as the model showed in the previous slide. You can see broadly similar information coming from the satellite in terms of the higher concentrations around Dakar itself, but there's also a little bit more information from the satellite in terms of these finer spatial differences in concentration. Also a little bit more noise in the satellite image due to presence of clouds and different effects interfering with the retrievals from the satellite. So the basic approach is that we would take the model and the satellite data together for some period of calibration time. Next slide, please. And we would derive calibrated or typical relationships between the two, also using other model information like the column concentration of NO2, which the model also estimates in addition to the surface level concentration. And between all these factors, we would identify typical relationships between these. So for example, is the model typically overestimating or underestimating the local concentration with respect to what the satellite is seeing at a finer resolution? Next slide, please. And then when we want to apply this to, for example, forecast air quality at a certain location or create a map for the forecast, We would start out with a model-based forecast, which Emma was discussing. Next slide, please. And we would impose upon that the same relationships we identified during the calibration period. So assuming those hold true into the near future, we would then create what's shown here, which is our first fused estimate, which is a combination of the model and the satellite information. So basically, the forecast is here being driven by the model, but it's being corrected, especially in terms of the sub-model grid scale variability using information from the satellite. Next slide, please. The next step would be to bring in surface monitoring data. So for example, we would have some surface level air quality monitors. In Dakar, there are a couple. I'm showing two sites, example sites here. And this basically allows us to do two things. First is connect the global and regional observations from the model and the satellite to the ground-based data to really do that bias correction. Here, we're not doing a separate bias correction for each site, but we're doing one bias correction for the whole region based on all the available monitoring data within our region. And the second is a little bit of a local updating in the immediate vicinity of these different monitors. So while our regional bias correction is correcting the bias on the regional scale, it still may be a little bit off in the local vicinity. So we do an additional local correction at each monitor site and then apply that in a small region of space around each monitoring site. Next slide, please. And the next step, I think you can go ahead one or maybe two more slides. Try the next slide and then one more slide. Yeah. So the next step would be to bring in, for example, low-cost sensor data in a lot of the application areas, especially in areas without an extensive regulatory monitoring network. Low-cost sensors are an important source of local information, and we could treat those in a similar way to the way we treat regulatory monitors. We would want to apply an additional step of verification to ensure that those low-cost monitors are performing adequately. But once we pass that verification, we can treat those similar to the way we treat the regulatory monitors to bias correct our fused estimates locally in the vicinity of those monitors. Next slide, please. And I think this is just going to show the performance of this on sort of a temporal basis. And the basic idea here is to see that as we move from the model by itself, which is the blue line, including the satellite data, moves us to the orange line, and then including the ground-based data from the regulatory monitors and low-cost sensors in those two purple lines, it's moving our estimates over this particular calibration interval closer to that green line, which is in this case the ground truth we're aiming for. This is still sort of a prototype version. Those are not the actual ground-based measurements. Those are some synthetic data that we generated just to test the method out. But you can see that it is working in the sense that it's moving our estimate closer and closer to that ground truth. So these are sort of encouraging preliminary results, and we're now working together with our partners to further refine this tool, bring in some of the actual regulatory and low-cost monitoring data from different networks in our partner cities, and really test out how well the tool is performing in those different areas. And again, just to sort of reiterate, so we've talked about earlier the bias correction method that's developed and implemented already in the CanAIRy Alert system, which is site-specific bias correction. This is now trying to use the satellite data as well to move to a more regional-based bias correction where we can provide forecasts not only for the specific locations that we have measurements, but a little bit in the regions around them as well.
Well, what I hope we've shown here today is that we have quite a mature global weather and composition forecasting system. Our products are, made available to the public since, everything we do is paid for by the taxpayers of America. And so we really have tried with the GEOS-CF to find file formats that are useful for both scientific research, but also some of these formats that are more useful for air quality managers, those that are working with that individual information. We are a research center. We're not, all of our stuff are research products. We don't have a backup supercomputer if anything does go wrong, which it doesn't usually, but these are just the type of things to keep in mind. But we we're really working on providing these downscaled, bias-corrected forecasts, and the work that Christoph developed with his machine learning algorithms, started several years ago, and it's just growing in its end user community. So we continue to develop this and try and find ways of getting the information onto more and more platforms for folks to use in different areas. And so we really want to hear from you what is useful, what isn't. We're quite nimble with our products. So if we need to add something like we really need PM10, like that's the type of thing that we love to hear. So hopefully working with WRI, we can, and everyone here in the room, we can really learn from each other to continue to make better and better products for folks to use. So thank you so much for listening. And we really, really do appreciate the invitation to speak with you today.
Thanks, Emma. Thanks, Carl. We have 10 minutes for questions and answers from the audience.
When the training started, when machine learning started to be used, there were a lot of pilot cities, including Bogota. We found it really helpful to show to politicians that we actually had problems that came from outside the limits of Bogota. Usually the administrators, the environmental authorities, normally they manage everything that is within their own jurisdictions, yet there are problems that cannot be addressed within those same borders. Thanks to this work, with all of these products, especially with forest fires, for example, we started getting more scientific credibility, so to speak, at a national level, and it is now cataloged as a temporal problem. It's a seasonal problem. It always happens at the same time of the year with the fires. And, while it's true what Emma was talking about some disadjustments in the model because of COVID-19, right? In Bogota, we still have not corrected for that. We hope to start working. We hope to start retraining the model soon. Also in terms of the emissions, because we have pretty good emissions. Just to give you some context, Emma. So besides the global tools at our disposal, we also have local computational capacity that allows us to run models with a higher resolution. This allows us to better understand the problems and to better respond to some problems that we couldn't address with the model originally, especially in some cities, some air quality stations, where the concentrations didn't really adjust to the model because there was more influence by local agents. At the end of the day, Bogota still uses this tool, just like many other tools. And we are using GEOS-CF data as border conditions for our local models. And this has allowed us for the forecast that the impact of forest fires in the city to be more accurate, to perform better. All of these tools, which are very visual, they're all very important because at the end of the day, decision makers, really what they understand is a map. When they see the hotspots, right? They say, oh, there's a problem here. We need to do something about this. So as a user of all of these tools, yeah, I can attest to the fact that they are indeed very useful. Even though, they have some technical limitations, but in spite of this, they give us a pretty good idea of problems that we face in our cities region. So that was really my comment. Thank you.
That is so encouraging to hear.
Thank you for that talk. I think my colleague has actually touched one of the things I wanted to speak about, and this was the forecast output. It's largely been presented in form of graphs and plots. So, but I think my colleague has talked about not transitioning it to other data analytics, including like color-coded maps and other ways, because I am looking at how you can use, how this forecast can be used as is, the direct output to be used by lay people, like some policymakers who do not have a lot of knowledge in air quality management, who may not necessarily understand the curves and how they move, but they will look at another visual that makes it very clear straight away whether I'm there to explain or not. So maybe you can comment about that.
I'm sorry, a plane flew overhead, so I missed a little bit of that. But Carl, you looked like you were shaking your head like you followed.
Yeah. So the comment about visualizing things with maps being sometimes easier than graphs, and I think that's a direction we're trying to move in. I think already the tools that Emma showed, the fluid visualization systems, those are from the model outputs, and they're more regional scale, but those kind of fulfill some of those functions. And then this is a global version of that map where you can zoom in a little bit closer. You are limited by the resolution of the model itself. I will also mention that on the previous slide, so those maps, you can also, it may be visible at the bottom, but there's an animation button. You can actually create an animation of the forecast, which will play as a little movie. So you can kind of see how the map's changing over the forecast lead time. So those are also a possibility just directly through the website. Oh yeah, Emma's got it.
Yeah, and you can I'll pull this up on my phone when I want to know. So like here, I want to choose all right, Central America. It takes a second because I pre-generated that this morning, but it'll take a bit of time, but then you can click on animate and it's making all of those pictures for you on the fly. So unless someone has done it before, it usually does take a bit of time for it to calculate it on the supercomputer, but then it'll start showing you the different images. And it's showing you every 3 hours, so the field is actually an hourly average NO2 map. But in this, you can see how the transport from different locations because of the wind flow. You can see in the NO2 the climatology of ship tracks. So those aren't live, but those are estimates. We can switch to a different species, and it will show you. And again, we can click on animate. You should be able to download the movie as well if you want to hold on to it and share it. But yes, it's definitely, pictures say 1,000 words, and especially if you can have a moving picture. But if there are things that you would like to see, those are the type of things we hope by working with end users we can help develop. And that's one of the things that with the project Carl and I and Christoph have with our different end users working on Google Earth Engine. A big part of that is going to be the user interfaces and making sure that they are designed for these specific applications that these cities have, but hopefully by going into different regions, we'll develop things that can be brought into more general use as well after the fact. So a lot of these times they start with those initial end users, like with the machine learning bias correction. It was a few cities that got excited early on, and now it's expanded to what we're talking about today.
Sorry. I'll do it one more time. Thank you, Emma and Carl, for the wonderful work that you are doing. I would like to also highlight on behalf of WRI that what we are trying to do after the CTAQ, what the work that was done that Edison saying that Bogota even right now is using those forecasts, we now try to translate that to African cities that could not set up a large network of reference grid monitors. But now we are going a step ahead of not only translating these tools to them, but also actively engaging them, because we might make those maps and deploy them on the Google Earth Engine and even Resource Watch. But you find that some of these offices may not really have the technical people to actually follow on with that and say that, hey, Carl, I would like to see a better visual or a finer visual of PM 2.5, or what does this mean for my city? So we are going like a step ahead to actually engage with these cities, and even sometimes alert them, hey, look at this forecast for tomorrow. What do you think? And then if it doesn't really turn out to be what will happen, cities that we are able to have that
very continuous feedback loop. So I look forward to seeing what you will do with this whole new data fusion technique, and also applying that in African cities, applying that in low resource environment, expanding that from Dakar to more cities that they have this data and it's open, and they're more than welcome to bring this work. Yeah.
Mm-hmm. Mm-hmm.
Yeah, that's definitely something we want to do. It's a little bit farther out for us, but I guess I didn't mention. So, we're using Dakar as our pilot, but we're working with the UN Environment Program, and the end goal is to sort of, once we have the system sort of developed, pass it over to the folks at the UN Environment Program so they can help other cities, get on board with using a similar system in their own context. So. The idea, really, to develop this so that it can be used in a lot of these other areas as well, beyond just the couple cities we're using as our test pilots.
Just wanted to follow that on with a question. So will you have, after developing this, a very open, like what you said in your previous presentation, where is it HA cast? You're able to have that continuous feedback from cities. What will be the channel for this? Right now it's in beta testing. So after this, how will we, as the people who are very interested, how will we keep on communicating and contributing to your work?
Yeah, so we'll have to see a little bit about how well this project goes, but the hope is that, if this project goes well, we might follow it on with further developments. The idea is, globally, to pass this off to the UNEP, the UN Environment Program. So I think that would be a good point of contact, to keep in touch with them, and help them understand who's interested in the system so they can connect. We aim to sort of develop this system in Google Earth Engine, which is kind of an open platform, and provide like the underlying codes and stuff available so people can, even without, maybe, UNEP will be there as a resource, but if people want to explore on their own, they'll have access to some of the basic underlying tools they need. And then I guess you mentioned HeyCast. I think that's a good point. This particular project is not being run through HeyCast, but there are similar other efforts going on within HeyCast, and in general, that's sort of HeyCast's mission, is to connect the scientists who are experts in these sort of systems with the end users, and really make those connections, as you were saying, with the end user needs, and make sure that what we're developing is really in line with those needs. So that's a goal of this project, which is not a HeyCast project, but it's closely related with a lot of other work that's going on at HeyCast.
Another important part of the work is obviously documentation as well. And through the NASA-Google partnership, with the initial getting the GEOS-CF and MER2 onto Google Earth Engine, one of our colleagues, Callum Wayman, designed this user interface to be able to downscale NO2 using Trapomi NO2 and the model NO2. And this type of thing, he'll provide a tutorial, like we're working on that right now. So these type of things, we're going to be working on making sure that the stuff that we do is well documented, that it can be reproduced by folks if they want to and interact. And so maybe along the way, these are the type of conversation that we can also, engage with WRI and keep folks engaged, because we definitely have this close relationship between our offices.
We have a couple more questions. One from the Jakarta Environment Agency.
While the formaldehyde is the good precursor of ozone, and so should we use formaldehyde as a proxy to estimate the ozone level using the remote sensing?
So yes, the example I showed uses both the formaldehyde and the nitrogen dioxide, and together the ratio of those is a proxy for ozone formation potential. This is again, not something that I've worked on directly. So we've shared these slides out, and in that particular slide, there's a paper that you can go to read a little bit more about the underlying methods that they use. So this is a paper, a fairly recent paper, kind of the state of the art of this technique, but this technique has been used a little bit more commonly. And the general idea is, as you mentioned, ozone cannot, usually surface level ozone cannot directly be observed with satellite products so easily, but the formaldehyde and especially the NO2 is a little bit easier. And this ratio between the two gives a sense of what the potential for formation is. It's still not directly the same as the ozone. It's only indirect information about the potential for ozone to form. There are a lot of other factors that are still important, but basically indicating, what the driving factors behind the ozone might be in different regions, whether it's more being driven by the NO and NO2 concentrations, or more by volatile organics, which formaldehyde is kind of serving as an estimate for or proxy for. So yeah, again, I'll just kind of direct you to that paper for some more details about the methods and then the limitations of the methods.
And Carl, correct me if I'm wrong, when it comes to the formaldehyde from OMI and TROP-OMI, to really get useful information from OMI, you have to average it over a long period, like a month. Whereas I think TROP-OMI, you can do shorter periods and still get something quite useful. But
yeah, they have some recommendations, I think, in the paper about that, and they say, certainly monthly, possibly with TROP-OMI going down to weekly could work.
Yeah.
But certainly not like day to day. I don't think that was recommended by them, at least. But yeah, that's a good point.
And it's one of the things that, I didn't mention it, but in our model, we're using a much older version for the GEOS than what's used in the current GEOS-FP. It's something similar to MERA-2. And we know it has a bias in its 2-meter temperature over the Southeast US. And our formaldehyde from biogenic emissions from the plants is driven by the temperature. So we overproduce formaldehyde in the Southeast US, which leads to an overproduction of ozone in our model. So there are things like this that we can then compare to satellite and say, like, oh yes, we really are overproducing formaldehyde at that scale. So it does definitely have its uses, even when OMI, you have to average it for a long period of time. It's a great question about the formaldehyde.
Yeah. So Jakarta basically has no experience on using the satellite as well as the forecast. So she would like to know what resource that needs to be prepared in terms of, for example, like computing resource or human resource, that what kind of skill that is needed to use the satellite and forecast.
Mm-hmm. I'll turn that probably over to Carl as far as like the amount of time one would maybe want to spend. The RSET trainings and the tools on Haycast are fantastic, but it does take time to go through that information. A lot of them are archived, so you don't have to do a live training, but it's still, taking the time like you've done today, this week, for trainings. Carl, do you want to speak to that?
Yeah, that's a good point. So I'd say in terms of the human capacity, I think I'm biased. I work for the RSET program, but I think it's a good program. You can go to the RSET website and look at, as Emma said, some of the historical trainings. I don't know specifically if we have one on this formaldehyde, but we do have a training on the OMI and the TROP-OMI products, satellites and the data products they provide. Which covers definitely the NO2. I think also they do briefly mention about the formaldehyde products. So that, in terms of human capacity building, I'd say to start with the RSET program. We have a range from sort of the introduction to remote sensing, which I gave a very condensed version of that at the beginning of my talk, but talking about sort of the basic concepts and then moving to more intermediate and advanced trainings on specific satellites, missions, instruments, and data products. And then in terms of physical infrastructure needs, Like I said, to get started, you can use some of the online resources like Giovanni and Worldview to do that. The only requirements would be a fairly robust internet connection with a personal computer to run some of those. All the computation is being done off-site with those. If you want to do more on-site analysis, there are analyses that can be done. When I started out, I used my personal laptop to do the analysis, and it takes maybe a few hours to run a more complicated analysis, but it can be done with sort of personal computers. If you're running these global models, as Emma said, you really need access to supercomputers, but the advantage with GEOS-CF is we're basically running it for you and we're making the outputs available. There are still some storage requirements in terms of downloading the data, and you can actually look at some of the file sites that Emma mentioned and get a sense of the file sizes for the data. So yeah, I guess she's bringing that up now.
Yeah, so like here you can get the time series information, you can get the surface maps, and then we have column maps. You can access the data. It gives you all the information here. And then to get to the interactive tool, you would click this button, so it's all accessible. And we can zoom in on Mexico City. You can move the map around. Oh, maybe we'll go over here. It's quite nice. Oh, wait, I wanted ozone. It'll take a second, it pulls it up. So there's a lot to play around. And then as you get more comfortable, you can revisit some of those training and tutorials. I've been working with the NASA data pathfinders recently. And so that is another website that we didn't highlight today so much, but they also have a great, I can make sure to send this to the group, and it'll give information and then how to find it and things like that. So it was last updated last year. Any day now, all of the work that we've done in the last couple of weeks will show up, and I'll have all of these links to tools and tutorials and case studies for folks to access. So once I see that's updated, I'll make sure that I send that to WRI.
Can I have one more question? It's from me actually. So I was seeing from your comparison with the Global Atmospheric Watch stations, but you had like really big box in Asia, all over from the north to the south. Just wondering that because Indonesia is one of the station.
Oh, like this one?
Yeah, one station for the Global Atmospheric Watch in Kota Tabang in our country. Does it also, and I also aware that the results shows the underestimate value for Asia. I just would like to make sure whether it represents the value from the northern part of Asia to the southern part of Asia, or it's represent for the specific region of Asia, because it's a different climate condition and others.
Yeah, so this was an evaluation of the model that we did when we first started running GEOS-CF. So it covers the period 2018 to 2019. And for those comparisons, it's using the available data in OpenAQ. And then for a couple of locations, we had collaborators that shared with us their data, such as some of the locations in Australia. So as you can see, for OpenAQ, these blue dots, it's mainly driven by the values that are here in China heavily. And yes, only you can see just a few blue dots in the southern portion of the Asia box. So if you're interested in more specifically the biases in your location, we'd really have to look at that one site and see how well that average, because I can definitely imagine how it might not be a fair assessment comparing the majority of which is on the mainland.
Thank you for your presentations.
Thank you. You guys were great. Really appreciate being here today with you.